would make this?
called a regio-specific reaction. Now, the easiest way to remember that is to say region-specific. I wish they had defined it that way, but they say regio-specific. Region-specific means something goes to a particular carbon, something else goes to another carbon. The stereospecific has to do with this anti or syn, but the regio-specific is the orientation thing, like Markovnikov's rule. And this, unfortunately, is a reaction that's both stereospecific and regio-specific. Unfortunate for students. It's not unfortunate to the reaction, because that specificity is desirable. I want to make a particular predictable product. Okay, and one last thing, well, actually two, but simple. Remember that this business of Markovnikov's rule doesn't matter if it doesn't apply. For instance,
Let's say one of those lines, dashes. I can't see that in between the CL and the
2-butene. If you add HCl to 2-butene,
What's that in the middle of that?
according
These
to
are big.
Markovnikov's rule, you would put the hydrogen on the carbon that already has more hydrogens. Obviously, Markovnikov's rule doesn't work here. And it's perfectly fine, because not only does this have the same number of hydrogens on both carbons, but it's symmetrical. So it doesn't matter where the H and the Cl go. In the case where you have the same number of hydrogens, but it's not symmetrical, there are two different results, depending upon how the H and the X add. But since this is controlled by carbocation stability, if the H goes here, your carbocation ends up there. If the H plus goes here, your carbocation ends up there. This carbocation is secondary, and so is this carbocation. So the reaction tends to not discriminate, and you do get a mixture. And what should tip you off is that when you try to apply Markovnikov's rule, it doesn't fit. In the top case, it doesn't matter. In the bottom case, it does matter that it doesn't fit, because you are going to get a mixture of the two products. The only time you don't get a mixture is if Markovnikov's rule fits. So watch out for that. And the other thing has to do with alkenes and this business of cis and trans. We've talked about cis and trans stereoisomers before, but cis and trans is limited in utility as a name. These are stereo descriptors. So for instance, this 2-butene is cis. 2-butene. The one below it is a different alkene. It's a stereoisomer called trans 2-butene. Now, they're not enantiomers. They're not mirror images. They're stereoisomers. Because the baked-in difference, three-dimensional difference, is due to restricted rotation, the called geometric. Isomers. They have different physical and chemical properties all the time.
His voice cracked again.
The trans is a little more stable than the cis, for instance.
He's gonna do
The
his second
cis
puberty.
is more polar than the trans. So there are rules, but generally, well, really always, stereoisomers like this are always different, so you have to respect them. Now, the cis and trans business doesn't always exist. For instance,
Too bad it wasn't on that. How do you know?
for one butene, there's two different drawings. These two geometric isomers. It's always obviously a trick question, so say no. They're not geometric isomers. And it's easy to spot that case when it occurs
Two methyl.
if either of the
Propane,
double bond
two.
carbons has two identical substituents. You can't have cis and trans isomers. What makes these two different is that to convert one into the other, you have to rotate. So if you have the cis, to get to the trans, you have to rotate around the middle double bond. And you can't do that because the pi bond is like a bicycle lock. Through your spokes on your bicycle holds them together. So they're permanently different. Now that's not the same thing as taking a structure like this and flipping it like a pancake. The whole molecule, I'm not rotating, my two fingers here are not
left one in the bottom
really
right.
rotating relative to each other. I'm just flipping the pancake over, or the hamburger. Same thing here. This is like flipping a hamburger. Take this whole molecule, flip it over, and it matches this one. Take this
guy's got
one,
excited
flip it
molecules.
over, and it doesn't match this one. So, a simple way again is make sure you have at least two different groups on each of the double bond carbons. They can match as they do in 2-butene, but on each of the double bond carbons, you need to have two different groups. So sometimes you do have stereoisomers, sometimes you don't. Now, let me give you an example, another example. Of an alkene that has 4 different groups on it. So that has a stereoisomer, it has a geometric isomer.
Yeah,
And I
they
can
have
write
that
it
too.
easily just by
Geometric.
doing what the molecule itself can't do,
Just the
rotating
C,
one of
right?
the carbons, but
Is it
not
like-
the other,
Did Honus start yet? Do you know?
180 degrees. So I left the left-hand double bond carbon frozen, and I flipped the other one, the right-hand double bond carbon, over like a pancake. Those are two geometric isomers. Which one is cis and which one is trans?
It's your question. We can't tell it up 3D. No.
Now, it's not exactly clear, is it? It's a little too complicated for cis and trans. Cis and trans really only works when you sort of have twin groups, like 2 methyl groups or 2 chlorines. Then it's clear communication when you
It's
say
CH3
cis.
because there's
This
no-
would
it's
not
not a
be
double bond.
clearly communicated as either cis or trans. That's where
You
the
could-
Z
you
and
could,
the
like,
E
guess.
comes in.
So it needs to be like.
Z and E is like the R and
So it needs
S
to have
on
this carbon has to
asymmetric
have
carbons, there's a set of rules for it, and Z
Has to
and
have 4
E
bonds
always work.
one
But
double
cis
bond
and
and 2
trans
bonds.
doesn't always work. So for this, you would have to use the Z and the E. If you can use the cis and trans, and you're pretty sure someone shouldn't be confused, go right ahead. But technically, the only IUPAC system is Z and E. Cis and trans is not
ICUP, what?
accepted in IUPAC. The Z and E always is.
The
Now, there's a set of
IUPAC.
rules.
I'm like, I hate
And it's not hard for
ICUP.
you to do that, follow the rules. But there's a procedure. You artificially divide the double bond in half. So now I've got 2 different carbons, double
Why
bond
even ask if
carbons,
it's cis or trans?
one on the left side of the
Irrelevant.
wall, one on the right side.
Where did they
You
come up with
assign
this stuff?
priorities to the
Who
groups,
cares?
really the atoms, on each of those Wolverine carbons. And you do it the same way as R and S. On the left, carbon is the first thing attached to the double bond there, and hydrogen here. So the top priority goes with the CH3, and the bottom priority goes with the hydrogen. Now, of course, with R and S, you have 1, 2, 3, and 4. But here you have just 1 and 2. 1 is the top priority, 2 is the bottom priority. Then you go to the other side, you look at the first atom directly attached to the double bond, and you can see this is 1 and this is 2. Now, if your ones match, that is, they're on the same side, that's the Z isomer. If the ones are on opposite sides, that's the E isomer. Now, there's more to the name, but I'm not gonna, it's a complex molecule, I'm not gonna bother with the
Thank
rest
you.
of the name. But in place of cis and trans, you would use Z blah, blah, blah for the top one, and E blah, blah, blah for the bottom.
Wait,
Now, Z is from the German word zusammen, which means together, on the same side. And E is from the German word entgegen, which
German.
means against or opposite. So Z and E always work.
Albrecht.
And you can see here that cis-2-butene is really Z-2-butene. A cis will always come out to be Z, and a trans will always come out to be E. So just so you're familiar with that. Okay, we're out of time. That's it. See you Tuesday. I'll be around if you have any questions. That's it.